All right, now when it comes to base ionizations, we can do very much the same thing. Equilibrium involving weak bases. The only difference is, so here's ammonia, which is a weak base. Ammonia reacts to give us NH4 plus and OH negative. We can set up our equilibrium expression again, but because H2O is considered a constant, we're going to rearrange, and we get, this time, because it's a base, we call it Kb. So Kb equals the conjugate acid times OH negative divided by the base. And we can solve the same kind of problems that we did with the acid. So here's our generic equation. Some base plus H2O gives us Hb plus OH negative. And our Kb is equal to Hb plus times OH negative divided by the concentration of the base. So conjugate acid times OH negative divided by the concentration of the base. And in the same way to acids, the bigger Kb is, the stronger the base is. We can solve a lot of the same problems in the same way. Here are some Kb values. Again, the larger the Kb, the stronger the base. If you're doing a homework problem and it doesn't give you the Kb, it's probably one of these on this chart. So let's just do a really quick problem. What is the pH of a 0.2 molar solution of pyridine in aqueous solution? Now, let me just back up. How do I know I need to set up an ice chart? It's because this is not one of the 6 strong bases. If it's a 6 strong base, then we don't need to set up anything, but if it's any other base, we have to set up an equilibrium. So, and they're telling you what Kb is. So, we're going to do the same things that we did before. We're going to set up the equilibrium, write the equation, make up an ice chart, table of concentration, set up the equilibrium constant expression, Kb, and this time we're going to solve, we still solve for X, but just keep in mind when you're doing bases, this is the only little thing you have to consider, is remember that X now equals OH negative, so you have to add one little extra step to find the pH, because you're going to end up finding the POH, and that's one a lot of people forget. So, all right, so here's our expression. Here's the base plus water, and if you're not sure, just stick an H on the front and make it positive. So there's our conjugate acid, OH negative. We set up our ice chart, 0.2 minus X, 0.2 minus X, X squared. We can do the same consideration for this. So if Cb over Kb is greater than 100, then again we can lose the minus X in the denominator. Or in other words, in this case, X is much smaller than 0.2, so it's negligible when subtracting. So if we plug those values, we get X squared over 0.2 minus X, but because Ca over Ka is greater than 100, ignore it. So now we're just going to solve this for X. Multiply both sides by 0.2 and then take the square root. So OH negative is 1.7 times 10 to the minus 5th molar. So if so now we can solve for POH. Don't forget X equals OH negative. So POH is 4.77, and then pH is 14 minus 4.77 or 9.23. Just take a minute and ask yourself. Remember, this is a basic solution, so your answer should be basic. Make sure and remember that last little bit. All right, so we're going to change gears a little bit and talk about acid strength, molecular structure and acid strength. So we do have charts that tell us which acids are stronger, but you can also sometimes look at the structure of an acid and determine, at least it relative to other acids, if it's stronger or weaker. So a couple of the things that we're going to, two of the things that are important in determining that is the polarity of the bond to which the hydrogen is attached, and then also Well, that's first. That's the polarity. So let me just back up for a second and say, remember that the stronger the acid, the more likely it is to give up, more likely to give up. So you can kind of see that the weaker this bond, the easier the H will be given away, which makes it a stronger acid. So the polarity of the bond is very important. So the more polarized the bond, the more, so technically the more negative the X is, the stronger the acid is. So the second factor, actually, it says the second factor is the strength of the bond, or how tightly the proton is held. Well, actually, that's the same for both factors, you know, because the more polar it is, the looser that bond is. But the second factor then is the size of the atom X. So if you think about, you know, H is attached to something small, or the bigger the other part gets, the looser that bond is going to be. So the larger atom X is, the looser the bond is, and the greater the strength. Now, sometimes these two factors oppose each other, and we have to consider which is more important. And so what we're going to do is we're going to look at binary acids, and then we're going to also look at oxoacids. So it turns out if you're talking about binary acid, and what is a binary acid? That's just when you have hydrogen and one other element. So HCl, HF, it doesn't have to be just one H, but just one other element. So H2S, H2O, etc. So as you go down the column of elements, radii increases, and so bond strength decreases, so the acid gets stronger. So acid strength gets stronger as you look, if you're looking at one column, and now again, you can't compare apples and oranges, but if you're looking at the same column, so HF is weaker than HCl, which is weaker than HBr, which is weaker than HI. So as you go down a column, you're getting stronger acid because the bigger the other atom is, the weaker that bond is. So it's kind of opposite what you might imagine, because polarity is the opposite. So polarity gets stronger as you go up, but acid strength gets stronger as you go down because of size. That's the most important thing. Now, as you go across the row of elements, polarity becomes the dominant factor. So as you go to the right, acid strength increases. So if you're looking at that second column, the second row, NH3 is a weaker acid than H2O, which is a weaker acid than HF. So as you're going to the right and as you're going down, acid strength. And this is for binary acids. Acid strength increases as you go to the right and you go down. So there you can see it. So CH4 is not really acidic or basic. NH3 is actually a base, H2O neutral, and then we get acidic. You get more acidic as you go down and as you go to the right. Now, if we have an oxoacid, which means it has a hydrogen and it has, generally speaking, the hydrogen is attached to an O. So it's got some element and it's got O's in it. And the H is generally attached. So that when I was talking earlier about acetic acid, the way the bond is, the C is attached to an O and then the H is attached to an O. So it depends on what E is, you know, so sometimes it depends on what E is. Sometimes the bond will break here, but sometimes the bond will break here. So bond B, it depends on what E is as to where this bond is going to break. So it depends on E. So it turns out that if the electronegativity of E is very low, then that means that bond A is polar. So these are examples, some examples of this would be, and so the OH will be broken off and these will be basic. So our example of that would be like sodium hydroxide, magnesium hydroxide, all of those metals that have low electronegativity. So that's why those metal hydroxides tend to be basic. Now, what about if E is electronegativity is high? So these are things like sulfur, phosphorus, nitrogen, chlorine, all of those. So if E has a high electronegativity, what's happening is holding on to that oxygen, and so actually, so the oxygen's held on tight to the E, and so what happens is this bond is the one that's breaking. So it's weaker and the hydrogen ions are released more readily. So things that are nonmetals have the high electronegativity, so they tend to be acidic. And a lot of times, and you'll notice like H2SO4, what we don't write on there is that actually it looks like this. The H's are technically bonded to an oxygen. We tend to not write it like that because it can get confusing because of the OH. But anyway, it's because S has a high electronegativity that these H's break off, leaving the O's with the S. So high electronegativities, oxo compounds tend to be acidic. Like I said, some examples: H2SO4, H3PO4. And then we can have if E tends to be intermediate, then that's when the compound can be amphiprotic, or it could be acidic or basic. So depending on if it's reacting with a strong acid or a strong base, bond A might break or bond B might break. So it depends. So in the presence of a strong base, the compound will act like an acid and bond B will break. But in the presence of a strong acid, it'll act kind of like a base, and bond A will break. And so metalloids and elements near the metalloids tend to have intermediate electronegativity. So like aluminum hydroxides and some others right there in the transition metals tend to be. Now, we're not really going to deal with those very much. What I'm showing you here is this compound. So it has some hydroxide, it has some water. It can act with bases to become to act like an acid, and it can react with acids to act more like a base. And like I said, we're not really going to get into this. It's the first two that you really should understand. So if we talk specifically about oxoacids, so those would be things like HClO or HBRO or things like that so they have an O and an H. We tend to write the H first because it's giving it up. So this is the bond that's breaking. When E has high electronegativities, this bond is strong, bond A is strong, and bond B breaks. So even more importantly, as the electronegativity of E gets larger, that makes bond B even more polar and so stronger acid. So as you go down a column with an oxoacid, the acid gets weaker. So remember, binary got stronger as you went down. So like HF was the weakest, and HI was the strongest, and HBr. And so these was the weakest and then strongest. But now, because electronegativity goes down, if you throw an oxygen in there, notice that the HOCl will be stronger than HOBr, which will be stronger than HOI. And HOF would be even stronger. So if it's got an oxo in there, it gets stronger as you go up the column. So let's write that down. Strength increases going up. And And then the final thing to remember is that the more O groups that you have attached, the more electronegative it becomes, and so the more acidic. So you can see here that nitrous acid, NO2, HNO2, is a weaker acid than HNO3. So if you add another O, it's more acidic. You can also, oxidation number also can tell you. So the higher the oxidation number, the more acidic it is. Same thing here, sulfurous HSO3 versus HSO4, which is a stronger acid. So oxo acids increase with more O's. And so in a similar way, HClO is weaker than HClO2, which is weaker than HClO3, which is weaker than HClO4. And then one last thing to remember is that, and I said this earlier, each successive hydrogen becomes more difficult to remove for polyprotic acids. And so with no hydrogens removed would be the strongest, and then one hydrogen removed is weaker, and then two hydrogens removed is weaker. So acid strength will decrease the more negatively charged that ion is.